We begin with the definition of an external direct product of groups. Let G1, G2 through Gk be groups. We can define group structure on the Cartesian product G1 cross G2 cross Gk in the following way. So if we take one n-tuple, so A1, A2, AK, and another B1, B2, BK, so here AIs and BIs belong to the group GI, then the multiplication is defined component-wise. So the result is A1, B1, A2, B2, AK, BK. So we multiply in each component. And clearly with this definition, the identity element is when we take identity in each component. And the inverse is also defined component-wise. We point out that we may identify each factor Gi with a subgroup in the direct product, G1 cross G2 cross Gk. For example, if we take the following subset, so we take G1 in the first component and then identity in all other components, and let G1 run over the first factor G1, then this will be a subgroup in the direct product isomorphic to the group G1. We point out that with this identification, the different factors will commute. So that is, so for all A in Gi and for all B in Gj, with I different from J, we have A times B is equal to B times A. Let us check this for k equals 2. So if we take A to be the element A1 identity and B be identity B2, then we have that both A times B is equal to A1 B2, and B times A is also equal to A1 B2. We point out that elements within the same component need not commute, so these factors need not to be commutative groups. The fact that different components commute implies that each factor Gi is normal in the direct product, G1 cross Gk. If each component Gi is finite, then the order of the Cartesian product is equal to the product of the orders of the factors. The operation of taking direct products is a constructor. So this allows us to construct bigger groups from smaller groups. But it also may be viewed as a deconstructor when we take a given group and try to decompose it into a direct product of its subgroups. This point of view on direct products is called internal direct product construction. Let us give the definition of internal direct product. Let G be a group with subgroups H1, H2, up to HK. So we say that G decomposes into direct product of these subgroups. So G is H1 times H2 times HK if the following properties hold. Factorization. For every G in G, there exists H1 in H1 and HK in HK, such that G is the product H1 times H2 times HK. Uniqueness. So this factorization given in the first property are unique. So this means that if we have H1, H2 times HK is equal to H1 prime, H2 prime, HK prime, with HI and HI prime in subgroups HI, then for all I, we must have HI must be equal to HI prime. So this says that the factorization given in the first property is unique for each G. And the third property is commutativity. So for all I different from J, if we have HI belongs to the subgroup HI and HJ belongs to the subgroup HJ, then the product HI, HJ is equal to the product HJ, HI. So we see an immediate corollary of this definition, that each subgroup HI is normal in G. So this follows from the factorization property that every element may be factored in this way, and commutativity. There is no difference between internal direct products and external direct products. So this is just a matter of a point of view. Here we are saying that if we take subgroups H1, H2, HK in the group G, and these subgroups satisfy these three properties, then G will be isomorphic to the external direct product of these subgroups. Let us make a couple of additional remarks. For k equals 2, so when we decompose a group into two factors, so the uniqueness condition is equivalent to the condition that these two subgroups have a trivial intersection. Indeed, if we write down the equality H1, H2 is equal to H1 prime, H2 prime, then this can be also written as H1 prime inverse times H1 is equal to H2 prime times H2 inverse. and we see that the left factor belongs to H1 and the right factor belongs to H2. So both will belong to the intersection H1 with H2. And if this intersection is trivial, so this means that both the left-hand side and the right-hand side is the identity element, and we conclude that H1 is equal to H1 prime and H2 is equal to H2 prime. When we have more than two factors, then we cannot simplify the uniqueness property in such a way. If the group G is finite and the uniqueness property holds, then the factorization property is equivalent to the condition that the order of the group is equal to the product of the orders of the factors. We point out that for this we even do not require commutativity property. Let us show this equivalence. So we consider a set S of all possible products. So we take H1 times H2 times HK, where each HI runs over the subgroup HI. Because of the uniqueness property, the size of this set is the product of the orders of the subgroups. And then, since we are told that the order of the group is also equal to the product of the orders of the subgroups, so the sizes of the sets S and G is the same, so this means that this set of products covers the whole group, and this shows the factorization property, that each element of the group may be factored as a product of elements from the subgroups. Let us give a couple of examples of direct products. Let us take the set Rn with operation of addition of vectors. So this is an additive group. Then this decomposes as R cross R cross R. So the additive group Rn is the direct product of n copies of the additive group of R. For our second example, let us take the multiplicative group of complex numbers. So these are non-zero complex numbers with respect to multiplication. And we claim that this group factors as the product of R plus star, so these are positive real numbers with respect to multiplication, cross S1, where S1 is the unit circle. So these are complex numbers with norm 1. And this factorization here is a consequence of the following claim, that any complex number, non-zero complex number, can be written in a polar form. So it can be written as R times e to the I alpha. So here R is the norm of this complex number and it will belong to R plus multiplicative, and e to the I alpha has complex norm 1, so this belongs to S1. If we restrict this example to real numbers, then we get that the multiplicative group of real numbers is isomorphic to R plus multiplicative times Z2, where Z2 is the sign subgroup, so it's plus minus 1. So this says that any non-zero real number may be factored as a plus minus 1 sign times a positive real number. For our next example, we recall the Chinese remainder theorem. That if the greatest common divisor of m and k is equal to 1, so these numbers are relatively prime, then the group Zm times k, the cyclic group Zmk, decomposes in the direct product of its subgroups, Zm cross Zk. This is actually a direct product not only of groups, but of rings. And because of this, we also have the same decomposition for multiplicative groups. So Zmk multiplicative is also factors as Zm multiplicative cross Zk multiplicative. Here the set Zm is the set of all multiples of k, and Zk is the set of all multiples of m. A generalization of this result is the classification theorem of finite abelian groups, that every finite abelian group decomposes into a direct product, or for additive groups, this is also called direct sum, of cyclic groups of orders that are powers of primes. We have the following theorem. Let G be a group with subgroups n and k such that 1, we have factorization property, for every G in G, there exists n in the subgroup n, and there exists k in the subgroup k, such that G is equal to n times k. Then we have the uniqueness property, that the intersection of n with k is the identity element. And the third property is that both n and k are normal in G. Then G decomposes into a direct product of n with k. Let's give a proof of this. So we need to show commutativity property. So that is for every n in n and for every k in k, we need to show that n times k must be equal to k times n. For this, we consider the commutator. So we take n times k times n inverse times k inverse. And we factor it in two different ways. So we write it as n times k times n inverse times k inverse. And we also write it as n times k times n inverse times k inverse. Because k is a normal subgroup, so the first factor, n times k times n inverse, belongs to k. And then we see that this belongs to k. And from the second factorization, using the fact that n is a normal subgroup, we see that this result also belongs to n. And so this implies that this commutator n times k times n inverse k inverse belongs to the intersection of n with k. But by uniqueness property, this intersection is identity. So this implies that n times k times n inverse times k inverse is identity, and this is equivalent to saying that n times k is equal to k times n. And we conclude that the subgroups n and k commute, and thus the group G decomposes into a direct product of n with k. Next, we're going to generalize the direct product construction by relaxing the commutativity condition. Let G be a group with subgroups n and h satisfying the following properties. Well, we have factorization. For every G in G, there exists n in n, and there exists h in h, such that G factors as n times h. 2. Uniqueness. So this factorization is unique, or equivalently, we can write that n intersection with h is identity element. And the third property is normality. And here we require that n is normal in G. If we say that both subgroups are normal in G, then we come to the situation of the direct product. But here we require that only one of these two subgroups is normal. Since n is a normal subgroup in G, G acts on n by conjugation. But here, instead, we're going to consider the action not of G, but of H. So we consider the action of H on n by conjugation. So we say that phi of H acting on an element n is equal to H times n times H inverse. And because n is normal, this will be in n. We know that conjugation by an element is an automorphism of the group. In particular, this tells us that phi is a homomorphism from H to the group of automorphisms of the group n. And this is the group homomorphism. Because of the first two properties of factorization and uniqueness, we can assign to each element G a pair, n and h. Just from this factorization, G is equal to n times h. So these components are uniquely defined. And then it will turn out that the homomorphism phi will encode the group structure in the group G. Indeed, if we multiply two pairs, n1, h1, and n2, h2, so this is just the product n1, h1 times n2, h2 in the group G. But then this product may be written as n1 times h1, n2, h1 inverse times h1 times h2. And then we can write this as a pair. So with first component being n1 times phi of h1 applied to n2, and the second component h1 times h2. And now we see that the group structure in G is encoded by multiplication in H, multiplication in N, and the homomorphism phi. This is the essence of the semi-direct product construction. Let us give its formal definition. Definition. Let N and H be two groups, and let phi be a group homomorphism from H to the group of automorphisms of N. A semi-direct product G, which is N semi-direct product with H, is the set of pairs. So G is the set of pairs NH, where N runs over N and H runs over H, with group operation so when we multiply two pairs N1 H1 and N2 H2, then the first component is N1 times phi of H1 acting on N2, and the second component is H1 times H2. Here the identity element is the pair where we take identity element in each component, and an exercise show that the inverse of an element NH is given by the following expression. So the first component is phi of H inverse acting on N inverse, and the second component is H inverse. And the second exercise show that this is well defined. That is, this multiplication that we introduced is in fact associative. Let us consider a couple of examples. Let's take G to be the dihedral group, Dn. Here we choose N to be the subgroup of rotations generated by an element R. So this is isomorphic to the cyclic group Zn. And H let be the subgroup generated by reflection T. So this is isomorphic to Z2. We know that for every G in the dihedral group, G may be factored as R to the power of K times T to the power of J, where K goes from 0 to N minus 1, and J is either 0 or 1. And we also know that the subgroup N is normal in Dn. Well, because it's an index 2 subgroup. Let us look at the conjugation action of H on N. So if we have T R to the power of K times T inverse, so this is equal to, we have the following relation in a dihedral group, that T times R is equal to R inverse times T. And because of this, so when we push T through R to the power of K, we get R to the power of minus K times T and T inverse, or the result is R to the minus K. This gives us a group homomorphism from H to the group of automorphisms of N, or from Z2 to the automorphisms of Zn, where for X in Z2, which is 0, 1, and for Y in Zn, we define phi of X acting on Y as minus 1 to the power of X times Y. With this homomorphism phi, we see that the group Dn decomposes in the semi-direct product of Zn with Z2. In this construction, we see that the subgroup N is normal in the dihedral group, but the subgroup H generated by reflection, this is not a normal subgroup. Thus, this semi-direct product construction is distinct from the direct product construction, and we see that these two subgroups do not commute. If in the definition of a semi-direct product we take the trivial homomorphism phi, where H is sent to the trivial automorphism of N for each element H in H, then the semi-direct product construction will yield the direct product construction as a special case. In our next example, let us take N to be a vector space with the vector addition as a group operation, and as H, let us take the group of general linear transformations on this vector space. We have a natural homomorphism from GLV to the automorphisms of V, where if we take A in GLV and the vector V in V, then we define phi of A applied to V as the product of a matrix with a vector, A times V. This allows us to construct the semi-direct product of V with GLV, and the group operation will be the following. So if we take the pair VA and multiply it by the pair WB, then the product of these two pairs is V plus A applied to W, and the second component is A times B, the product of two linear transformations. This semi-direct product has the following geometric interpretation, that G is the group of affine transformations of the vector space V. So now, with each pair VA, we associate a map T from V to V using the following formula, that T applied to a vector X is V plus A times X. So we can easily see that T is not a linear transformation. In particular, so T of X is equal to V, and this is not necessarily 0. But let us compute a composition of two such transformations. Suppose we also have another affine transformation, S of X, which is W plus B applied to X. So what is the composition of T with S applied to X? So this is going to be T applied to S of X, which is W plus BX. And now when we apply T to this, then we're going to get V plus A times W plus BX. And this is equal to V plus AW plus A times B times X. And what we see is that this is exactly the semi-direct product. So we have the first component, which is V plus AW, and the second component, which is A times B. Let us give one more example. If we take N to be the additive group Zn, and H to be the multiplicative group of Zn, then we can take G to be the semi-direct product of N with H, because H is isomorphic to the group of automorphisms of n. And this isomorphism gives us a natural map from Zn multiplicative to the automorphisms of the additive group of Zn. And then multiplication in the group G is like this. So if we take A1, B1 and want to multiply it by A2, B2, so here A1 and A2 are from the additive group, and B1 and B2 from the multiplicative group, then this is the first component is A1 plus B1 times A2, and the second component is B1 times B2. So this will be the semi-direct product structure on G. We can summarize the discussion that preceded the definition of the semi-direct product with the following theorem. Let G be a group with subgroups N and H such that G is finite and the order of G is equal to the order of N times the order of H. 2. The intersection of N with H is trivial. And 3. N is normal in G. Then G is a semi-direct product of N with H. So by considering the action of H on N by conjugation, we will obtain the homomorphism phi from H to the group of automorphisms of N, and we recover the group structure on G from the semi-direct product construction. We point out that in the semi-direct product construction, if we take the quotient of G by N, then this quotient is isomorphic to H. Indeed, from the factorization property, we know that G can be written as the union of cosets with respect to N. So we can write it as a union over H and H, N times H. And this will give the isomorphism between these two groups. And in conclusion, we make another remark. That suppose we have a group G with a normal subgroup N. And let H be the quotient group, G by N. If we can realize H as a subgroup in G, which is complementary to N, so that is, if we can factor G as N times H, then we get a semi-direct product construction. But if this condition does not hold, so that is, we cannot find H as a complementary subgroup inside G, still we can ask the question, so can we recover the group structure on G from the group structure on N and the group structure on the quotient group? And so here, to recover G from N and the group H, which is G quotient by N. So here we apply the machinery of group cohomology. But this is a different story.